Think about the sheer volume of water moving through a modern high-rise at any given second. Hidden behind the drywall and concrete is a massive, highly pressurized circulatory system moving thousands of gallons vertically into the sky. To design this system, engineers use a simple mathematical baseline. Total water demand, represented as Q, equals the population of the building multiplied by per capita usage, or LPCD. If you leave that per capita number up to guesswork, the math breaks down. You either over-engineer a system that costs millions of dollars too much, or under-engineer one that runs dry. You need a rigid, universally agreed-upon statistical anchor. For standard residential buildings, the National Building Code establishes exactly what that anchor is. It dictates a baseline requirement of 135 liters per person per day. We are going to deconstruct that exact 135-liter metric. We will map its internal distribution and track how this single number forces the specific physical sizing of every tank, pipe, and sewer line in a structure. Standardizing human behavior into a single fixed number allows engineers to build reliable physical infrastructure at a massive scale. But to understand the physical pipes, we first have to look at what a statistical human actually does with their 135-liter daily allotment. If we break that volume apart, we see it divides into specific daily tasks: bathing, washing clothes, kitchen use, and toilet flushing. Exactly 60% of all daily domestic water demand is driven by just two activities: bathing and toilet flushing. Compare that to the extremely low volume actually consumed. Only about 10% of the daily allowance is used for drinking and cooking. This severe statistical imbalance drives modern engineering codes. Since most human usage does not require drinkable water, the code requires a separate plumbing system for potable and non-potable water. Treating an entire building's water supply to expensive, high-purity standards is mathematically inefficient when the vast majority of human activity requires zero purification. Let's apply this baseline to a standard 30-unit residential block housing exactly 150 people. 30 flats multiplied by 5 persons per flat times 135 liters per capita equals a total daily water demand of 20,250 liters, or 20.25 kiloliters per day. If humans behaved like machines, usage would be perfectly distributed across a 24-hour period, but humans operate on routine. Water use violently spikes at 7 a.m. when everyone wakes up to shower, and again at 7 p.m., leaving pipes dormant overnight. To account for this temporal chaos, engineers use a core mathematical multiplier called the peak factor. The code mandates a peak factor range of 2.0 to 3.0 for residential structures to handle the intense morning rush. If we take our average hourly demand and apply a 2.5 peak factor, the required flow rate jumps to 2,109 liters per hour. This calculated extreme peak rate becomes the actual discharge variable used to physically size the primary distribution pipes. Designing for the statistical average guarantees fluid systems will fail under pressure. They must be physically built to withstand the absolute extremes of human routine. The math changes again when we zoom in from the primary building supply lines down to individual floors and specific bathrooms. The localized challenge is sizing a specific pipe feeding a bathroom, where a shower and a sink and a toilet might all activate at the exact same time. To model the statistical probability of these overlapping events, localized calculations rely on the demand factor, or D factor. The formula calculates the square root of the number of fixtures, -1, to determine maximum simultaneous demand. Individual appliances get statistical weightings called fixture units. A flush valve water closet requires a heavy 5.0 rating, while a simple wash basin demands 1.0. Applying the D factor prevents catastrophic over-engineering. It relies on the statistical proof that not every single tap in a building will open at the exact same millisecond. As pipes get closer to the human endpoint, their physical diameter is dictated less by the total volume of the building and entirely by the localized probability of overlapping events. Once the water is used, the system has to handle the final, inevitable phase of the cycle, outflow. This introduces a rigid, codified mass balance rule linking clean supply to waste. By standard definition, sewage generation equals 80% of the water supply. Applying this to our 30-unit test building directly converts the 20,250-liter daily input into a required 16,200-liter daily sewage output. While incoming supply lines are highly pressurized, the sanitary drainage tasked with handling this 80% return volume relies strictly on gravity. The human input statistics permanently lock in the geometry, slope, and diameter of the entire sewer architecture before a single drop of water ever enters the building. We can now zoom out and view this entire building ecosystem, unifying the clean input, the pressurized internal movement, and the gravity-fed outflow into one continuous engine. This chart shows the complete block diagram of a structural water supply system. The initial 135-liter per capita metric dictates the exact physical footprint of the massive underground and overhead storage reservoirs. The 2.5 peak factor maps directly onto the distribution network, dictating required pump horsepower and riser pipe diameter. Finally, the 80% return rate exits the fixtures, defining the sanitary exit path that completes the cycle. Physical plumbing geometry is nothing more than a codified wrapper for human behavior. By translating human unpredictability into rigid statistics, engineers ensure systemic safety, hydraulic efficiency, and urban sustainability.